Chapter 3 Basic Execution Environment. This chapter describes the basic execution environment of an Intel 64 or IA32 processor, as seen by assembly language programmers. It describes how the processor executes instructions and how it stores and manipulates data. The execution environment described here includes memory, the address space, general-purpose data registers, segment registers, the flag register, and the instruction pointer register. 3.1 Modes of Operation. The IA32 architecture supports three basic operating modes: Protected Mode, Real Address Mode, and System Management Mode. The operating mode determines which instructions and architectural features are accessible. Protected Mode. This mode is the native state of the processor. Among the capabilities of Protected Mode is the ability to directly execute Real Address Mode 8086 software in a protected, multitasking environment. This feature is called Virtual 8086 mode, although it is not actually a processor mode. Virtual 8086 mode is actually a protected mode attribute that can be enabled for any task. Real Address Mode. This mode implements the programming environment of the Intel 8086 processor with extensions, such as the ability to switch to protected or system management mode. The processor is placed in Real Address Mode following power up or a reset. System Management Mode, SMM. This mode provides an operating system or executive with a transparent mechanism for implementing platform-specific functions, such as power management and system security. The processor enters SMM when the external SMM interrupt pin, SME hash, is activated or an SME is received from the Advanced Programmable Interrupt Controller, APIC. In SMM, the processor switches to a separate address space, while saving the basic context of the currently running program or task. SMM-specific code may then be executed transparently. Upon returning from SMM, the processor is placed back into the state prior to the system management interrupt. SMM was introduced with the Intel 386TM-SL and Intel 486TM-SL processors and became a standard IA32 feature with the Pentium processor family. 3.1.1 Intel Registered Signed 64 Architecture. Intel 64 architecture as IA-32E mode. IA-32E mode has two submodes. These are, Compatibility Mode. Submode of IA-32E mode. Compatibility mode permits most legacy 16-bit and 32-bit applications to run without recompilation under a 64-bit operating system. For brevity, the compatibility submode is referred to as compatibility mode in IA32 architecture. The execution environment of compatibility mode is the same as described in Section 3.2. Compatibility mode also supports all of the privilege levels that are supported in 64-bit and protected modes. Legacy applications that run in Virtual 8086 mode or use hardware task management will not work in this mode. Compatibility mode is enabled by the operating system OS on a code segment basis. This means that a single 64-bit OS can support 64-bit applications running in 64-bit mode and support legacy 32-bit applications, not recompiled for 64 bits, running in compatibility mode. Compatibility mode is similar to 32-bit protected mode. Applications access only the first 4 GB of linear address space. Compatibility mode uses 16-bit and 32-bit address and operand sizes. Like protected mode, this mode allows applications to access physical memory greater than 4 GB using pay physical address extensions. 64-bit mode. Submode of IA-32E mode. This mode enables a 64-bit operating system to run applications written to access 64-bit linear address space. For brevity, the 64-bit submode is referred to as 64-bit mode in IA32 architecture. Volume 1 3:1. Basic Execution Environment. 64-bit mode extends the number of general-purpose registers and SIMD extension registers from 8 to 16. General-purpose registers are widened to 64 bits. The mode also introduces a new opcode prefix, REX, to access the register extensions. See Section 3.2.1 for a detailed description. 64-bit mode is enabled by the operating system on a code segment basis. Its default address size is 64 bits, and its default operand size is 32 bits. The default operand size can be overridden on an instruction-by-instruction basis using a rex opcode prefix in conjunction with an operand size override prefix. Rex prefixes allow a 64-bit operand to be specified when operating in 64-bit mode. By using this mechanism, many existing instructions have been promoted to allow the use of 64-bit registers and 64-bit addresses. 3.2 Overview of the basic execution environment. Any program or task running on an IA32 processor is given a set of resources for executing instructions and for storing code, data, and state information. These resources, described briefly in the following paragraphs and shown in Figure 3:1, make up the basic execution environment for an IA32 processor. An Intel 64 processor supports the basic execution environment of an IA32 processor, and a similar environment under IA-32E mode that can execute 64-bit programs, 64-bit submode, and 32-bit program. Compatibility submode. The basic execution environment is used jointly by the application programs and the operating system or executive running on the processor, address space. Any task or program running on an IA32 processor can address a linear address space of up to 4 GB, 232 bytes, and a physical address space of up to 64 GB, 236 bytes. See Section 3.3.6 Extended Physical Addressing in Protected Mode for more information about addressing an address space greater than 4 GB. Basic program execution registers. The 8 general-purpose registers, the 6 segment registers, the FLEX register, and the EEP instruction pointer register comprise a basic execution environment in which to execute a set of general-purpose instructions. These instructions perform basic integer arithmetic on byte, word, and double word integers, handle program flow control, operate on bit and byte strings, and address memory. See Section 3.4 Basic Program Execution Registers for more information about these registers. X87 FPU registers. The 8 X87 FPU data registers, the X87 FPU control register, the status register, the X87 FPU instruction pointer register, the X87 FPU operand data pointer register, the X87 FPU tag register, and the X87 FPU opcode register provide an execution environment for operating on single precision, double precision, and double extended precision floating point values, word integers, double word integers, quad word integers, and binary coded decimal BCD values. See Section 8.1 X87 FPU execution environment for more information about these registers. MMX registers. The 8 MMX registers support execution of single instruction, multiple data, SIMD operations on 64-bit pack byte, word, and double word integers. See Section 9.2 The MMX Technology Programming Environment for more information about these registers. XMM registers. The 8 XMM data registers and the MXCS are register support execution of SIMD operations on 128-bit pack single precision and double precision floating point values, and on 128 pack byte, word, double word, and quad word integers. See Section 10.2 Intel Registered Sign SSE Programming Environment for more information about these registers. YMM registers. The YMM data registers support execution of 256-bit SIMD operations on 256-bit pack single precision and double precision floating point values, and on 256-bit pack byte, word, double word, and quad word integers. Bounds registers. Each of the BND0, BND3 registers stores the lower and upper bounds, 64 bits each, associated with the pointer to a memory buffer. They support execution of the Intel MPX instructions. BNDCFGU and BinStatus. BNDCFGU configures user mode MPX operations on bounds checking. BinStatus provides additional information on the hashtag BR caused by an MPX operation. 3.2 Volume 1, Figure 3:1, IA32 Basic Execution Environment for non-64-bit modes. Basic Execution Environment. Basic Program Execution Registers. Address space, 2 to the power of 32-1. 8 32-bit registers, 32 bits. FPU registers. General Purpose Registers. Segment registers. FLIX register EEP. Instruction pointer register. 6 16-bit registers. 32 bits. 8 80-bit registers. 16 bits. 8 64-bit registers. 16 bits. 16 bits. Floating point data registers. Control register status register. Tag register. 0. The address space can be flat or segmented using the physical address extension mechanism. A physical address space of 2 to the power of 36, 1 can be addressed. 4 128-bit registers. 48 bits, 48 bits. Opcode register. 11 bits. FPU, instruction pointer register. FPU data. Operand, pointer register. MMX registers. XMM registers. YMM registers. Bounds registers. MMX registers. 32 bits. BND, C, FGU. XMM registers. MXCSR register. YMM registers. Bin status. 8 128-bit registers. 8 256-bit registers. Volume 1 3 Basic execution environment. Comma. Stack to support procedure or subroutine calls, and the passing of parameters between procedures or subroutines. A stack and stack management resources are included in the execution environment. The stack, not shown in Figure 3:1, is located in memory. See Section 6.2 Stacks for more information about stack structure. In addition to the resources provided in the basic execution environment, the IA32 architecture provides the following resources as part of its system-level architecture. They provide extensive support for operating system and system development software. Except for the I/O ports, the system resources are described in detail in the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volumes 3A, 3B, 3C, and 3D. All ports. The IA32 architecture supports the transfers of data to and from input-output I/O ports. See Chapter 19, Input-Output, in this volume. Control registers. The 5 control registers, CR0 through CR4, determine the operating mode of the processor and the characteristics of the currently executing task. See Chapter 2 System Architecture Overview in the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volume 3A. Memory Management Registers. The GDTR, IDTR, Task Register, and LDTR specify the locations of data structures used in protected mode memory management. See Chapter 2 System Architecture Overview in the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volume 3A. Debug registers. The debug registers, DR0 through DR7, control and allow monitoring of the processor's debug and operate. See in the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volume 3B. Memory Type Range Registers, MTRRs. The MTRRs are used to assign memory types to regions of memory. See the sections on MTRRs in the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volumes 3A, 3B, 3C, and 3D. Model-Specific Registers, MSRs. The processor provides a variety of model-specific registers that are used to control and report on processor performance. Virtually all MSRs handle system-related functions and are not accessible to an application program. One exception to this rule is the time stamp counter. The MSRs are described in Chapter 2 Model-Specific Registers, MSRs, of the Intel Registered Science 64 and IA32 Architecture Software Developers Manual, Volume 4. Machine check registers. The machine check registers consist of a set of control, status, and error reporting MSRs that are used to detect and report on hardware machine errors. See Chapter 16, Machine Check Architecture, of the Intel Register Science 64 and IA32 Architecture Software Developers Manual, Volume 3A. Performance monitoring counters. The performance monitoring counters allow processor performance events to be monitored. See Chapter 20, Performance Monitoring, in the Intel Registered Science 64 and IA32 Architecture Software Developers Manual, Volume 3B. The remainder of this chapter describes the organization